Hello, my name is Tony Lentz, and I'm going to cover the topic of how surface finish affects solder paste performance. First, I'll give you a brief introduction on the concept behind this work. Then I'll go through our experimental methodology, and I have a lot of results to discuss with you. And from those results, we've drawn some conclusions, and we can make some recommendations for surface finish and solder paste combinations that'll work best for you. And then I've got a bunch of future work planned based on this experiment. And then instead of taking questions and answers, obviously because this is a recording, please email me if you have any questions. My email address is shown on the first slide and also on the last slide of this presentation. So we're talking about 6 different surface finishes in this work. OSP, or organic solderability preservative, ENIG, which is electroless nickel immersion gold, HASL, which is hot air solder level with a tin lead alloy, and we have a lead-free version of that HASL coating, immersion tin, and immersion silver coatings. These surface finishes obviously have to work together with solder paste in order to create a quality solder joint. So the question is, how do these different surface finishes affect solder paste performance? Here's a pie chart of surface finish use from a couple of years ago. Now these are sales dollars and not like chemistry consumption values, so keep that in mind. Here's the ENIG surface finish, which is the largest slice of the pie, so that's the most popular finish on this chart, followed by immersion tin, which is the green pie piece, and then OSP is the red pie piece, and that's followed by immersion silver. And then the thin blue piece here is ENIPIG, which is rising in popularity, and then the smallest piece of the pie is HAL, or hotter level coatings. Here's the experimental methodology that we used to run our testing. These are the 6 different surface finishes that we're testing. Tin lead HASL, lead-free HASL made with a lead-free alloy comprised of copper, nickel, and germanium with a tin base. High temp OSP, ENIG, immersion tin, and immersion silver. And the thicknesses were measured for the hotter level coatings to these values. So the hotter level tin lead coating ranged in thickness pretty widely, ranged from 1.6 to 8.4 microns, so it was fairly bumpy. It wasn't very planar. The lead-free HASL coating, by comparison, was a lot more flat. It ranged in thickness from 2.8 to 3.3 microns, which isn't always the case. It is still a HASL coating, so there's still a risk of puddling and pooling. But for these particular test boards, which are fairly simple in design, it blew a lot flatter and a lot more uniform than the tin lead coating. And the rest of these thickness values are all standard values for the different surface finishes. Here are the 4 different solder pastes that we used in this testing. We've got water-soluble and no-clean tin lead solder pastes, and then water-soluble and no-clean SAC 305 solder pastes. The names that I'm using in the rest of the presentation for these solder paste combinations are shown here. The solder powder size that we used was IPC type 4. Here's a picture of the test board that we used for this experiment. This is called the PR test board for measuring print and reflow properties. So it can measure printed solder paste limits. The area ratios on these patterns range from 0.30 up to 0.50, so incredibly small area ratios, which you wouldn't normally try to print solder paste through. And that kind of measures the drop-off limit of where the paste will print or not print onto these surface finishes. Then we have 0.4 millimeter pitch BGA arrays here, which are used to measure transfer efficiency numbers, solder paste volumes. There's a lot of pads here, so we can gather a lot of data points very quickly on these test boards. We can measure wetting or spread percentage using this pattern, graping percentages using these patterns, and solder balling using these pullback patterns. And then voiding was measured on these QFN component thermal pads. Here are the print parameters that we used for this testing. All of the stencils were made of 5 mil thick, fine-grained stainless steel. And this is a picture of what the stencil design looked like. Here are the 2 different reflow profiles that we set up for this. This is the tin lead profile, and this is the SAC 305 profile. These are both linear ramp to peak type profiles, and the measured data on these profiles are shown here for reference. Reflow was done in a 10-zone convection oven with an air atmosphere. Here's the process that we used to create the test boards and to gather data from these test boards. So we printed the solder paste, measured solder paste volumes, placed the QFNs and reflowed the test boards. We took pictures of the solder joints. We tallied up the reflow data, and then we measured voiding underneath the QFN thermal pads. And then we repeated this. We made 10 boards for each combination. There are 6 surface finishes and 4 solder pastes, so there's 24 total combinations. And then from that, the data that we gathered were transfer efficiency and coefficient of variation in both the 0.30 to 0.50 AR limit patterns and the 0.4 millimeter pitch BGA arrays. In terms of reflow, we measured wetting percentage, solder balling, and graping percentage. And then in terms of voiding, we measured void area and the size of the largest void. Here's an example of the type of statistical analysis that I used in some parts of this presentation. We're going to show data as box plots in some cases. In terms of the box plot, the median or middle value is shown by the line in the middle of the box. The box itself represents the middle 50% of the data points. And then the minimum value is the bottom whisker and the maximum value is the top whisker. And here's an example of a statistical analysis that we run called a Tukey-Kramer on a significant difference test. This test allows you to compare data sets to each other and determine whether they are significantly different or if they are statistically similar. So for example, we have transfer efficiency here for the 4 different solder pastes. And if you look at these box plots, they're all pretty wide. These ranges are pretty wide. And if you just visually compare these with your eyeball, you'd say, you know, maybe the tin lead water-soluble paste has a lower volume than the others, but is it significant? There's a lot of overlap here. So it's hard to say just intuitively by looking at these box plots, which is why we run this Tukey-Kramer HSD test. So the Tukey-Kramer HSD test spits out this connecting letters report, which gives you the mean values, and it assigns letter codes to each data set. If the letter codes are different, then the data sets are significantly different with a 95% confidence level. If the letter codes are the same, then they are statistically similar. So in this case, the water-soluble sac paste had a higher transfer efficiency than all of the others, and that was significantly higher. Both of the no-cleans are statistically similar, and then the water-soluble tin lead had the lowest overall transfer efficiency, and it's significantly lower than the others. So here are the results. These are the transfer efficiency results broken out by solder paste on the left and surface finish on the right. In terms of solder pastes, we just looked at the same Tukey-Kramer analysis. So the water-soluble sac gave the highest overall transfer efficiency. Both of the no-cleans were very similar, and the water-soluble tin lead is the lowest transfer efficiency overall. In terms of surface finish, there were some differences in print performance as well. The ENIG and HASL finishes gave the highest transfer efficiency, and those were significantly higher than lead-free HASL and OSP, which was significantly higher than immersion tin and significantly higher than immersion silver. Now this was not expected. I thought all of the flat surface finishes would perform pretty equivalently in terms of transfer efficiency, but they didn't. Immersion tin and immersion silver had lower solder paste volumes than all of the others. Oh, and I should note that this data includes all 4 of the solder pastes are included within each one of these box plots. Here's how the area ratio limit patterns work, generally speaking. So you've got transfer efficiency here and the different area ratios increasing up to 0.50 here. So at the 0.30 and 3.5, you can see very low transfer efficiencies, 5 to 15%. And that gets progressively higher with increasing area ratio, as you would expect. This is the 0.50 area ratio pattern, which is pictured here. And then you've got the BGA arrays for comparison. And you get a little bit more volume out of the BGA arrays because those are normal etched pads with a solder mask clearance around them. And so there's some standoff, there's some off-contact printing going on in the BGA arrays, which is not present in these area ratio patterns because you're printing on essentially a big ground plane here. But the whole point of using these is to see kind of where the lower limit is. And some solder paste just will not print at these really low area ratios. So this really challenges solder paste, particularly in terms of printability. Here's the transfer efficiency data for the 0.50 area ratio patterns. You've got transfer efficiency on the y-axis, and then the 4 different solder pastes are the major categories here, and then the box plots are different colors for the different surface finishes. Now I just want to point out that there is a lot of variation here. Look at the no clean tin lead paste. There's a lot of difference in transfer efficiency for these different surface finishes. And that's true for most of these pastes. The water-soluble SAC paste shows a little less variation. It prints somewhat equally well on all of these surface finishes. Now I highlighted in red the HASL surface finish, and in green the immersion silver surface finish. The red HASL surface finish had the highest overall volumes in this pattern. The green immersion silver surface finish had the lowest overall volume in these patterns. Here's the same type of data for the 0.4 millimeter pitch BGAs, which happen to have a 0.50 area ratio as well. Again, there's a lot of variation here within each paste, except for the water-soluble SAC, which seems to print pretty equivalently well on all the finishes. ENIG is highlighted in blue in this case, and immersion silver in green. So the ENIG surface finish gave the highest overall transfer efficiencies for each of these solder pastes, and the immersion silver was the lowest overall for each solder paste. Here's a summary of transfer efficiency and coefficient of variation for the 0.4 millimeter pitch BGAs, separated by surface finish. Here's the mean transfer efficiency data, the standard deviations, and then the coefficient of variation. So coefficient of variation is a measure of variability in the process, and the goal is to have a CV value of less than 10%. Only ENIG matched that goal or went below that goal. HASL, immersion tin, lead-free HASL, and OSP all had values between 10 and 16% coefficient of variation, which isn't great, but it's definitely better than the immersion silver, which had a coefficient of variation of over 20%. So that means that there's a lot of volume variation when printing on immersion silver for these 4 solder pastes. Here are the reflow test results. Here's the wetting data. I'll briefly explain how the wetting pattern works. So this wetting pattern has parallel lines with 15 bricks of solder paste printed down each line. Those spacings range from 0.1 millimeter in the center to 0.4 millimeter on the outside. And then during reflow, all those bricks merge together to form smooth continuous lines, as what's shown here. This is ideal wetting performance, or 100% wetting is the goal. So this is the wetting data broken out by solder paste, including all of the surface finishes. No clean tin lead and water-soluble tin lead both wetted almost 100% on all the surface finishes, whereas the no clean SAC was down around 70 and the water-soluble SAC was down around 80% for all the surface finishes. Here's that same wetting data broken out by surface finish. It includes all 4 solder pastes within each bar. So ENIG, immersion tin, and lead-free HASL all wetted very easily. They all had 100% wetting, followed by HASL and immersion silver, which were around 80%, and then OSP was the lowest overall wetting with about 55% spread. And here's some pictures to show that OSP wetting or spread. So this is the no clean SAC on OSP. These bricks pretty much stayed right where they were printed. They didn't flow very much. Whereas with a no clean tin lead solder paste on that same OSP finish, you get good wetting or spread where the bricks merge together very well. Here's the wetting data for each surface finish and solder paste combination. So the surface finishes are shown in the major categories, and then each solder paste is broken out within those. So ENIG, immersion tin, and lead-free HASL again had near 100% wetting regardless of solder paste. HASL had some variations. So in terms of the HASL, the tin lead solder paste had 100% wetting, and the lead-free solder pastes had 50 and 62% wetting. Immersion silver had some variation as well. Water-soluble SAC wetted at almost 100%, followed by the no clean tin lead. Then the water-soluble tin lead and the no clean SAC was the lowest wetting on immersion silver. And then if you look at OSP, it had the widest variation of all the finishes. Both of the tin lead pastes had near 100% spread, whereas both of the lead-frees were down around 10 to 15% spread. And these 2 pictures at the bottom kind of show the best case and worst case scenario. You've got lead-free HASL with water-soluble SAC, 100% spread or wetting, and then the OSP with the no clean SAC. You can see these bricks didn't merge together very well. They pretty much stayed right where they were printed and didn't spread on those lines. So the wetting percentage was 11% in that case. Here's the solder balling data. So the solder balling patterns work like this. There are 20 mil diameter pads on the circuit board surrounded by solder mask. We overprint onto the solder mask between 500% and 1250% over the size of those pads. And then during reflow, those pull back into a central sphere, and then we inspect the flux pool for solder balls. And we're talking about microscopic random solder balls here. We measured solder balling in 3 performance categories. We measured the largest overprint that had 0 solder balls, the largest that had less than 5, and the largest that had less than 10 solder balls. And then we gave them a rating. And so the goal is 1250%, which is the largest overprint. If you hit that rating, then that is best possible performance. So here's solder balling broken out by solder paste. In general, the no cleans and the water-soluble tin lead all had very good solder balling performance, where the water-soluble SAC did not have very good solder balling performance. Here's that same data broken out by surface finish. ENIG, HASL, lead-free HASL, OSP all had excellent solder balling performance. Immersion silver and immersion tin were a little worse in terms of solder balling, a little bit lower data here. And here's an example of what we're looking at. Here's the OSP with water-soluble tin lead. You can see some rings of solder balls in these flux pools. Here's the graping data. Here's how the graping test pattern works. There's 4 columns of pads, both circles and squares, non-solder mask defined and solder mask defined, and they change in size. So the size of the pads ranges from 7 mils up to 12 mils, and the area ratios on the stencil correspondingly are 0.35 up to 0.60. So really small area ratios again, which challenge the printability of the solder paste. And the lower volume deposits tend to be susceptible to graping during reflow. The goal here would be to have 0% graping. So the graping looks like this picture below. So you can see these larger deposits are very smooth and well formed, and then the smaller deposits here have clearly graped deposits. Here's the graping data broken out by solder paste, including all finishes. No clean tin lead was the lowest, followed by water soluble SAC, then water soluble tin lead, and then no clean SAC had the highest graping, generally speaking. Then the graping broken out by surface finish, you've got ENIG and HASL, which are the lowest, followed by lead-free HASL and OSP, and then immersion silver and immersion tin gave the highest overall graping. And this includes the data for all of the solder pastes. Here's the graping for every combination of surface finish in each measure category and solder paste broken out for each line. Again, you see variation on these finishes. So generally speaking, ENIG and HASL had pretty low graping numbers, but there's some variation based on these different solder pastes. Immersion silver had high graping with most of the pastes, but low graping with the no clean tin lead. And immersion tin had high graping with most pastes, but low graping with the water soluble SAC. And then the lead-free HASL had pretty wide variation, and the OSP again had the widest variation. So the no clean tin lead paste on OSP gave almost 0 graping, whereas the no clean SAC gave 45% graping, which is the highest overall graping. Here are the voiding test results. So in terms of voiding, what we're doing is we're printing solder paste in a 9-window pane pattern on the QFN thermal pad, placing these QFNs, which have a matte tin finish. The body size on that's 10 millimeters across. And the goal here would be to have 0% void area, but that's not what we got. So we got some voids that look like these pictures below. Here's the voiding broken out by solder paste. Water-soluble tin lead is the lowest, followed by no clean tin lead, no clean SAC, and then the water-soluble SAC is clearly higher here. The Tukey Kramer analysis validates that. Water-soluble SAC is the highest voiding with 28% void area, followed by no clean SAC, which is 11% void area. Then no clean tin lead is 7%, and the water-soluble tin lead was as low as 4% void area. And that includes data for all the surface finishes. So there's clear differences in void performance based on solder paste. Here's the voiding data broken out by surface finish, including all of the solder pastes within each surface finish. Immersion silver has the lowest overall voiding, followed by a combination of ENIG, HASL, lead-free HASL, and it looks like OSP and immersion tin are the higher end voiding. But there's a lot of overlap here in these data sets. So looking at the connecting letters report, immersion tin had the highest overall voiding, and that was significantly higher than all of the others. Then ENIG through HASL here have the same letter code, so they're all statistically similar. And then OSP through immersion silver all have the same letter code, so those are all statistically similar. Immersion silver did have the lowest mean, but it's statistically similar to the 3 surface finishes above it here. So the voiding differences based on surface finish are a little less clear than they were by solder paste, but there are some differences. Here's the voiding for each combination of surface finish and solder paste. You've got void area here on the y-axis, the different solder pastes in the major columns, and then broken out within that are the different surface finishes. You see pretty good void performance for the no-clean tin lead and the no-clean sac, generally speaking. The overall lowest void performance was the water-soluble tin lead with most of the surface finishes. And then the water-soluble sac gave higher voiding and had the overall highest combinations with 3 of these surface finishes. Here's some pictures that show that example pretty well. So here's immersion tin with the water-soluble tin lead paste, only 9% void area. Nice low voiding. That same immersion tin finish with water-soluble sac, solder paste on it, the void area jumped up to 46%. Immersion silver was run with the same water-soluble sac paste and it only had 8% voiding, so very low voiding. Immersion silver with the water-soluble tin lead solder paste dropped down as low as 3% void area, which is the lowest overall combination for voiding. Here's the scoring system. I came up with a scoring system to try to sort out these combinations. I wanted to quantify what was the best set of solder paste and surface finish combinations and which were the worst surface finish and solder paste combinations. So here's the way I set up my scoring system. So I measured performance in these 9 different categories. I've got 4 print categories, 3 reflow categories, and 2 void categories. I assigned a total possible score of 5 points. 1 would be the lowest score, 5 is the highest. And then I tallied up the scores for each of these combinations, and the total possible is 45 points for each surface finish solder paste combo. Here's the actual scoring system that I used. Here's the different scores. Again, 1 is the lowest or worst performance, 5 is the highest or best performance, and here are the metrics that I used to rank performance. Here are the overall scores for surface finish and solder paste. So in terms of surface finish, Enig and HASL performed the best overall. That's tin lead HASL, followed by OSP and lead-free HASL in the middle. And then immersion tin and immersion silver had the lowest overall scores in terms of surface finish. In terms of solder paste, the no-clean tin lead outperformed the water-soluble tin lead, which was similar to the no-clean sac. And then the water-soluble sac was the lowest overall scoring solder paste. Here's the total set of scores of every surface finish and solder paste combination. Here's the print score, the reflow score, the voiding score, and the total out of 45. And these are ranked from highest to lowest. So at the top, you've got OSP, no clean tin lead, Enig, no clean tin lead, lead-free HASL with no clean tin lead, and so on. If you look at the top 10, there's 7 tin lead solder pastes, 3 Enig finishes, and 3 HASL finishes. Then if you look down at the lowest scoring combinations, you got lead-free HASL with water-soluble sac, OSP water-soluble sac, immersion tin water-soluble tin lead, immersion silver with no clean sac, and so on. There are 7 sac solder pastes in the bottom 10, 3 immersion tin and 3 immersion silver surface finishes. So generally speaking, the tin lead pastes outperformed the sac solder pastes. Enig and HASL outperformed the immersion tin and immersion silver surface finishes. And the other combinations were in the middle. Here's that same set of scores, but these are blocked together, grouped together by surface finish. So within each surface finish grouping, they're sorted from highest to lowest score so that you could pick a surface finish and solder paste that had the best possible scores. Of course, if you look at these, you've got Enig with no clean tin lead, HASL no clean tin lead, immersion silver, water-soluble tin lead, and so on. Like the tin lead pastes are the highest scoring. So if you have to use lead-free, then you'd have to move down a little bit and say, okay, Enig with water-soluble sac is a good combination, HASL with no clean sac, and so on and so forth. Here's an overview of all of the scores. So this is an overview of surface finish performance. Here are the surface finishes that I tested in terms of printing, reflow, and voiding performance. So Enig had good print and reflow performance, but it was not very good in terms of void performance. Tin lead HASL was okay or moderately performing across the board. Immersion silver was pretty poor with print and reflow, but it was excellent with voiding performance. It was the lowest overall voiding surface finish. Immersion tin was moderate with print and reflow and not so good with voiding. It had one of the highest overall voiding numbers. Lead-free HASL was not so good with print, was very good with reflow and voiding performance. OSP was good with printing, not so good with reflow, and it was okay or moderate with voiding performance. So from all this data, here are the conclusions that we can draw. The no-clean tin lead solder paste worked well with most of the surface finishes, but the no-clean SAC 305 would be the best lead-free option for the surface finishes that we tested. Enig and tin lead HASL worked well with most of the solder pastes, so if you have a choice to choose your surface finish, I would recommend one of those two. Immersion tin and immersion silver did not perform as well as the other finishes, and that was a little surprising to me. I expected better performance out of those two. They need to step it up next time. And then OSP and lead-free HASL gave a wide range of performance depending on the solder paste. In some cases, their performance was excellent, and in other cases, it was not very good. So the performance of these combinations definitely depends on both the solder paste and the surface finish that you're using. Here are recommendations. We would recommend you run a similar evaluation in your process with your surface finishes and your solder pastes. And if you have the ability to change your surface finish, I'd recommend you pick a couple that work well with the paste that you're using. Or vice versa. You can't change the surface finishes, but you can pick your solder paste. Pick some solder paste that work well with all of the finishes that you use. Now, one thing I should say is that surface finish and solder paste varied pretty dramatically by manufacturer. Obviously, I used our solder paste in this experiment. You use solder paste from one of our competitors, they're going to perform a little differently in this testing. That's why I'd recommend you run a similar evaluation. And in terms of surface finish, two different circuit board manufacturers with the same process and the same chemistry from the same supplier might run them differently. And they might have different process controls. So you might get different results on the surface finishes from two different board suppliers. So I'd recommend that you test your surface finishes from each board supplier that you deal with. I know that sounds like a lot of work, but it's the only way to really be sure you're going to be able to predict performance of those surface finishes with your solder pastes. And then here I listed combinations that actually work the best for us, and I picked the best performing tin lead and the best performing lead-free for each surface finish from our experimentation. The future work that I've planned on this is I would like to explore additional combinations of surface finish and solder paste. I want to include other lead-free alloys besides SAC 305. I'd like to run some testing on tin silver and possibly tin bismuth alloys. The print parameters will be varied to some different print speeds and maybe different blade pressures to see how that affects printability. I will also vary the reflow profiles a little more widely. In this case, I just used linear ramp to peak profiles. I would like to use some soak profiles and possibly high peak temp or long time above liquidus type profiles. I'm sure that'll have an effect on some of these surface finishes. And then reflow performance will be measured on the second cycle to simulate double-sided surface mount work. So I'll thermally stress the boards one time through the oven, then I'll print and reflow and measure data on the second pass through the oven. I'm sure that'll damage some of these surface finishes and show us pretty different performance. Thank you for your attention. Thank you for listening to this presentation. If you have any questions, you can contact me at the email address or telephone number below. Thank you again and have a great day.